So chapter 2 is concerned with measurements, and first of all we're just going to reiterate as to why measurements are important in science. So measurement is measuring the dimensions or the capacity or the quantity, or if you want, the extent of something. And the scientific method is heavily reliant on measurements. Typical measurements that we're going to make in the lab will be things like the volume of a liquid or solution, the temperature of an object, the length of an object, the mass of an object, or the pressure of a gas. All measurements have at least two parts. The first part is a number called the magnitude. And that tells you how big the thing is that you're measuring. And then the second part is units. And the units tell you what is being measured. Sometimes we include extra things in order for the measurement to make sense, like the direction. And you can consider this if you think about if you're giving directions to your house. If you were to say, oh, I live 30 miles away, that's not very useful. But if you say I live 30 miles north of campus, then suddenly that measurement has a real meaning. The other thing that we'll often include when we're giving the value of a measurement is an estimate of the variance. And sometimes this is done using what we call plus or minus notation. So here you can see I've written that we've got today's maximum temperature was 27.5 plus or minus 0.2 degrees Celsius. The magnitude is the 27.5. The degrees Celsius is the units. And then this plus or minus 0.2 is what we call the variance, and that tells us that our value was somewhere between 27.3 and 27.7. So the take-home thing here is that chemists collect what we call quantitative data by making measurements. Typical things that we'll measure will be mass, volume, length, temperature, and pressure. Every measurement has a size that tells you how big the measurement is, and then units that tell you what is being measured. You may also include other things such as a distance or a measure of the variability of your measurement. There are two types of numbers that we commonly will encounter in science. One class of numbers are what we call exact numbers, and the other are inexact numbers. So exact numbers are numbers that have no uncertainty associated with them. And the classic example of this is a whole number of objects. So when I look at these 3 pennies, there really is no doubt that there is exactly 3. There isn't any possibility of there being 4, and there's no possibility of there being 2. There is exactly 3. So the 3 here is an exact number. The other very common exact number are unit definitions. And so these are exact because we made them exact. We defined them to be exact. So there is exactly 12 inches in a foot or 10 millimeters in 1 centimeter. A very rare example of where we might want a number to be known as being exact is when we use a simple fraction. So in science, if I write a simple fraction of 1/2, I want that half to be considered exact. So for example, 1/2 of a centimeter would be 5 millimeters. And if I wanted that to be recognized as being an exact number, I would use the simple fraction rather than 0.5. I've got to be honest here and say I've never seen anybody use a simple fraction to express that a number is exact, and I've only ever seen examples of exact numbers of the first 2 types. Inexact numbers are numbers that have some uncertainty associated with them. Every measurement is an inexact number. And the reason why is because there will always be limitations of the person making the measurement and the device being used to make the measurement. So for example, this is a ruler here that measures every 100 centimeters. So you can see that any measurement that is made with this ruler is going to have a little bit of uncertainty about it. So this blue line here falls around about the 300 centimeter mark, but not exactly. So the value that where this line falls is, there's some uncertainty about how well we know what it is because of the quality of the measuring device we are using. So exact numbers are unit definitions and whole numbers of objects. They have no uncertainty associated with them. Inexact numbers are measurements, and they have some uncertainty associated with them due to limitations of the device used to make the measurement, and also due to the limitations of the person making the measurement themselves. Three terms that are associated with measurements are accuracy, precision, and error, and they have very specific meanings in science. This little chart here, which is often described as being darts and arrows, where we have precision on the y-axis and accuracy on the x-axis, is often used to explain the difference in the terms precision and accuracy. Accuracy is a measure of how close our value is, our measured value, to the true value. And when we have more than one measurement, it's associated with the average. So you can remember that average for accuracy, they both start with an A. So this collection of arrows here is highly accurate because they are all very close to the bullseye. This collection of arrows here is also highly accurate because on average they are very close to the bullseye. We have some that are a little bit too high, but we have some that are a little bit too low, and as a result the difference is cancelled out and the average would be exactly in the middle here. This group of arrows over here is not accurate at all. The average is sort of right there in the middle of the cluster, and that's way off the center of the target. Similarly with these guys, we have three that are sort of to the left and too low, and then we've got this one out here. The average is probably sort of in here. Again, we're missing the target and we have low accuracy. Precision is a measure of how close a collection of measurements are to each other. So these guys here are all very close to one another, so they are highly precise. And these guys here are quite scattered, so they are not so precise, they have low precision. And these four here have really bad precision, they're all over the place. And again here we have four arrows that are really closely grouped together, and so we have high precision over here. So high precision doesn't mean high accuracy, and vice versa. Accuracy is related to how close our measurement or the average of our measurement is to the true value. Precision is how close a group of measurements are to each other. So why do we get less than perfect accuracy or less than perfect precision? The reason is because of systematic and random errors. Systematic errors are those that cause our measurements to be either all too big or all too small. That is, they vary in a consistent fashion. So if you weigh an object and every time you weigh an object it always turns out to be 2 pounds heavier than what it really is, then that's an example of systematic error. How we eliminate systematic error is by calibration. We need to correct this scale here and make it 2 pounds lighter. Random error is when we get some measurements that are a little bit too big and some measurements that are a little bit too small. The reason that we get random error is due to the limitations of the person making the measurements and also limitations to due to the quality of the device. We really can't do anything about it. These types of errors are what we call uncontrollable. How we get rid of random error or we reduce random error is we take a large number of measurements and we average them. And hopefully we have as many that are too high as we do that are too low, and the errors kind of cancel out. So here's a typical question where you're being asked to comment on accuracy and precision. It says we have 3 manufacturers of printed circuit boards. They are asked to prepare circuit boards that have copper lines that were 1.500 micrometers wide. Each of the manufacturers prepared 3 samples, and the data on the measurements of those 3 samples is presented below. So manufacturer 1 had 3 samples where they were all a little bit too big. Yeah, they were all a little bit too big. Manufacturer 2 had 3 samples where we have one that's too small and 2 that are too big. And then manufacturer 3 had 3 that were all too big. So if we think about this, which manufacturer was the least precise? And so that means what one had the greatest spread amongst their measurements, and it's pretty clearly number 1. They're spread by as much as 0.006. So that's going to be manufacturer number 1. Then it says, what manufacturer was the most accurate? Well, this guy was, up to 0.012 away from the desired value. These were all within 0.001 of the desired value, and these were way off. So it's going to be number 2 that is the most accurate, that's closest to the desired value. Now, when we look at precision here, which manufacturer was the most precise? So that means what manufacturer had the measurements that were closest to one another. And that's going to be manufacturer 3 because they were identical measurements. And then finally it says which manufacturer has large systematic error with little random error. And so we're looking for a manufacturer that has all of the values either being too big or too small. So that narrows it down to number 1 and number 3. And number 3 has the largest systematic error. Now, little random error means that we don't have values being too big and too small. So it's going to be number 3 here. Number 3 has very little random error. In fact, they all have exactly the same systematic error and no random error at all. So that's going to be number 3. Okay, so what does all of this mean? Accuracy is an indicator of how close a single measurement or the average of a series of measurements is to the true value. Precision is a measure of how close a series of measurements are to one another. Systematic errors are when we have all of our values being either too big or too small in a consistent fashion, and we can correct for systematic error through calibration. Random error is when our values are sometimes a little bit too big, sometimes a little bit too small. Random errors are the result of the quality of our measuring device and how skillful the person is that's making the measurements. How we reduce random error is by taking a large number of measurements and then averaging the results and hoping that our errors cancel out.